This video, we're going to talk about techniques for computing limits. This is going to be part one of two for this. This set of objectives are going to discuss techniques to compute limits conceptually. We're going to compute limits and state the limit laws used to justify computations. We're going to evaluate two-sided limits using limit laws and theorems. We're going to evaluate one-sided limits using limit laws and theorems. We're going to evaluate limits using factorizations. We're going to identify and discuss several important limits, exponentials and trigonometric functions specifically. And if you're following along in the textbook, that this is from section 1.3. So whenever we get a limit that we're trying to evaluate, we always want to start with algebra and arithmetic. First, so assume the problem is simple until we know otherwise. So the first thing we're going to want to try always, all the time, is direct substitution. That'll be our first technique here. So this is an algebra technique. All right, so we have developed a conceptual understanding of limits. Many situations will arise where either our previous techniques will fail or we won't have a visual of a graph readily available. So in this section, we'll learn some analytical methods. For evaluating limits. And this should just be super exciting to you as a math major. If you are a math major, to know that there's ways for you to get the answer here and get the exact answer and not have to draw a picture, because we know in math that pictures can be great for lots of things, but they're not good for proofs because our pictures are not perfect. So first thing we want to try is direct substitution, like we were talking about up there with arithmetic. And then second thing that we want to try is some kind of algebraic manipulation. This may be factoring. It may be rationalizing the numerator or denominator by multiplying by the conjugate. You'll know more what I mean when we get into some examples here. But when we take limits of linear functions, then we're going to be able to use direct substitution, since those linear functions are going to be continuous everywhere. So let a, b, and m be real numbers for linear functions. Y equals mx plus b. The limit as x approaches a of f of x equals f of a, which is going to be m times a plus b. So this is a direct substitution. Of x equals a. We're going to know that we can do that for linear functions and really all polynomials. When we talk a little bit more about this idea of continuity, we've talked about certain types of discontinuities already, but we haven't formally defined what it means for something to be continuous. We're getting there. We need to finish our discussion of limits before we can formally introduce the concept of continuity. But informally, I'm going to tell you that if you can draw that section of the graph without picking your pencil up off the paper here, which you can do with a line, that it's going to be continuous at that part of the graph. And if it's continuous there, then you're going to be able to use direct substitution, no problem. So more on that later. So this is true for most elementary or basic functions, things that are continuous. So we really will let that sit for a little bit. We'll come back to that maybe in like our sixth video, I think, is where we're going to pick up on this idea of continuity and what it means for a function to be continuous or piecewise continuous or whatever. So hang on to that thought about if the function is continuous or piecewise continuous at a, then we'll be able to make direct substitution there with x equals a. But let's go ahead, knowing that we can do this with linear functions, let's go ahead and just direct substitution here and evaluate. And 1/2 times -3 minus 2 is -3 halves, minus 6 halves is a -9 halves. I'm sorry, this is 4. This is 2/1, and we multiply by 2/2 to get halves. That's -4 halves is a -7 halves. And then when we have no x in it, this is a linear function, but it's constant. It's always going to equal the same value from the left and the right. This is f of 100 is going to be a constant 5. So if we want to look at that graph there, y equals 5. Here we have 0, 1, and we can come all the way out here to 50. We can come all the way out here to 100. And as I get close from the left and the right, we're staying close to y equals 5 on both sides. So we'll talk about limits at infinity later, but this would be a good example of it doesn't matter. I can go all the way out there to the biggest number that I want to the right, and this is still going to be 5. I can go out to the biggest number to the left over here that I want, and it's still going to be 5. So let's not concern ourselves too much with that. And yeah, I did the work up there for the first one already. So here's our limit laws that we're going to want to know, that the limit of the sum is the sum of the limits here. The limit of the difference is the difference of the limits. If we have constant multiples inside of a limit, those constants can pass through the limit symbol and we can multiply on the outside. And we need to watch out specifically for product and quotients of limits, because even though I'm just going to make this note, you'll understand more what I mean by this in chapter 2, that derivatives are going to be special kinds of limits and they'll inherit a lot of these laws. They won't inherit these 2 laws right here. That won't work. We'll have special rules for the product and quotient rule for derivatives, but powers here, if I have a function raised to a power that I want to take the limit of, just take the limit of the function and raise it to that power. That should work. And then also, since the roots are special types of powers, that limit as x approaches a of f of x raised to the 1 over n is equal to limit as x approaches a of f of x raised to the 1 over n, provided that special consideration here that f of x must be greater than 0 for all x near a if n is an even number, because we'll have an even root and square roots, fourth roots, so on, have to have us have x greater than or equal to 0. Equal to 0 would be okay, because the nth root of 0, whether it's even or odd, is always going to be 0. We'll talk more about that later. So that's not a big one right now. But evaluating limits, let's suppose the limit of f of x as x approaches 2 is 4, limit of g of x as x approaches 2 is 5, and limit of h of x as x approaches 2 is 8. So we want to take the limit as x approaches 2 of f of x minus g of x over h of x. So this should be limit as x approaches 2 of f of x minus limit as x approaches 2 of g of x divided by limit as x approaches 2 of h of x is going to be 4 minus 5 over 8 is a negative 1/8. Note, it is important to recognize the limit as x approaches 2 of h of x is not equal to 0. If it was, there wouldn't be an answer, because I'm not allowed to divide by 0 and the limit would not exist. So let's go ahead and do this one. So 6 times limit as x approaches 2 of 6 times f of x times g of x plus limit as x approaches 2 of h of x is going to be 6 times the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x plus the limit as x approaches 2 of h of x. I'm going to come back up here and say 6 times limit as x approaches 2 of f of x we defined as 4. Limit as x approaches 2 of g of x we defined as 5. Limit as x approaches 2 of h of x we defined as 8. So 20 times 6 is 120, plus 8 is 128. Now let's go on here and say if I have the limit of x approaches 2 of the quantity g of x cubed, then this is going to be the limit as x approaches 2 of g of x. Quantity cubed is going to be 5 cubed is going to be 125. When given expressions for f of x, g of x, h of x, direct substitution will give these answers also. We just don't have the expressions for f of x, g of x, and h of x in this problem. We just have the limits given to us. But Moving on, and I mentioned this already, polynomial functions are continuous over their entire domain. As such, if f of x is a polynomial, then the limit of f of x as x approaches a is going to be f of a. Rational functions, which would be the ratio of polynomials, typically contain discontinuities. Therefore, when evaluating the limit of a rational function, be cautious of problem spots, spots that are not in the domain, but the rational function is going to be piecewise continuous. So it's just going to be broken up into intervals that I can draw without picking my pencil up off the paper, whether those stop at holes or at vertical asymptotes and so on. So the limit of f of x over g of x as x approaches a, this limit is equal to f of a over g of a only if g of a is not equal to 0. Remember, division by 0 is invalid. Limits of polynomial and rational functions assume p and q are polynomials and k is a constant. So limit as x approaches k of p of x is equal to p of k, and limit as x approaches k of p of x divided by q of x is equal to p of k divided by q of k, provided that q of k is not equal to 0. If q of k is equal to 0, use another technique like algebra to see if you can get that factor that's going to 0 in the denominator to cancel out with the same factor in the numerator. So now that we are speaking of that, let's see if we need to do that in any of these rational functions here. So first things first, let's try direct substitution if we can. So this is going to be 3 times 2 squared minus 4 times 2 over 5 times 2 cubed minus 36 is equal to 3 times 4 minus 8 over 5 times 8 minus 36 is equal to 12 minus 8 over 40 minus 36 is equal to 4 over 4, which is 1. And that's a rational function. Example. Okay. Another example here. Evaluate limit as x approaches 4 of x squared minus 9 is going to be equal to 4 squared minus 9. 16 minus 9 is 7. That was a polynomial example. And now we're going to have to deal with an algebraic function. Limit as x approaches 2 of the square root of 2x cubed plus 9, close the square root, plus 3x minus 1 over 4x plus 1. We're going to try direct substitution first and see what happens. The square root of 2 times 2 to the third plus 9 plus 3 times 2 minus 1 over 4 times 2 plus 1 is 2 times 8 plus 9 plus 6 minus 1 over 8 plus 1 16 plus 9. This is plus 5 on the outside. This is a 9 in the denominator. Square root of 25 plus 5 over 9 is 5 plus 5 over 9 is 10 over 9. So later we'll have to be careful with functions involving the square root. But in this case, direct substitution worked. Notice that we have not actually evaluated limits where the denominator of a rational function is 0 yet. So if that happens, we're going to use algebra. We're going to simplify by factoring, if possible. We're going to multiply by some form of 1. To change the way the expression looks. Or we're going to maybe use identities. You might need to multiply by form of 1. That might be using the conjugate technique that we talked about before. But let's consider the function f of x equals the square root of x, and we take the limit as x approaches 4. What are we going to do? We're going to use the we can use the graph here if we want to. Let's look at the graph. Say 1, 2, 3, 4 has this point here, 4, 2, 1, 1, 4, 2, and it's continuous right there at x equals 4. And so we're going to say that this is 2. But we have a legitimate question here about what happens, what do we say about 0 here? And textbooks actually do not agree sometimes with what to do with 0 there. So since we do not have behavior from the left, and we say that the limit from the left and the limit from the right need to equal one another, then some textbooks would say that the limit does not exist. Others would say, well, okay, but this graph is continuous on its domain, and its domain is from 0 included to infinity. So we want to, if it's continuous at 0, then it needs to have a limit at 0, and we just know that the limit doesn't come from the left-hand side, it only comes from the right-hand side, and we only consider the right-hand limit. That's up to the textbook that you're using. So looking at roots here, how we're going to deal with them in this class, limit as x approaches a from the right of f of x if for 1 over n, if n is a positive or is an even number. We're only going to deal with the right-hand behavior when we talk about the limit. We can talk about the left-hand limit here for x near a with Well, we're going to see. So let's go ahead and look here. So we're going to say here that this limit does not exist. But as a special case, we're going to think about here limit as x approaches 0 of the cube root of x. If that index was odd instead, that's going to be just plain old 0 because we have activity from the left and the right. So again, I'm going to say that this limit for this square root function up here does not exist because it doesn't come from the left. If your teacher tells you differently, your textbook tells you differently, you do what your teacher and your textbook tells you to do. I'm going to say that if you're there at that vertex of this even root, then you need to be able to come from the left and the right for the limit to exist. So think of tracing the graph with your pencil and approaching x equals a. What value is your pencil approaching? Let's look at a piecewise function here. And come back up here. We'll say that this was 2 and that this does not exist. All right. So if x is less than or equal to 1, we're going to find the limit as x approaches 1 from the left. It's going to be -2 times 1 plus 4 is -2 plus 4 is 2. And the limit as x approaches 1 from the right equals the square root of 1 minus 1 is 0. And they're not the same thing. So therefore, the limit as x approaches 1 of f of x does not exist. You want to see that with a graph. There's a jump in the graph at x equals 1. We have 1, 2, and 3, 4. It comes up like this. And then we have 1, 0. And we have the square root function. Like so. 4, 2, yep. So like so, and there's this jump in the graph there that's going to make the limit not exist because we come at different values from the left and from the right. We don't approach the same value. All right, let's go ahead and consider the following graph and the indicated limits. As I approach 0 from the left, that does not exist. As I approach 0 from the right, we're getting close to 3. 1 from the left here is getting close to 4. 1 from the right, we're also getting close to 4. So as I come from the left and the right there, the limit is 4. 3 from the left, we're getting close to 0. 3 from the right, we're getting close to 1. So that limit, as we get close to 3, does not exist because those limits are different from the left and the right. 2 from the left, we're getting close to 3. 2 from the right, we're also getting close to 3. limit from the left and the right is 3. Don't get mixed up with the fact of what the function value is. Ignore the function value when you are finding the limit. So when we discuss continuity later in section 2.6, it'll be important for you to further examine whether the function is continuous at these places. Anywhere where the limit does not exist, it automatically won't be continuous. Just because the limit exists, like at 2, does not mean that it's continuous, because I have to pick my pencil up off the paper to draw that hole and to draw that that point that is removed from the rest of the graph. So we'll come back there. Other techniques for evaluating limits are factor and cancel, or general algebra, and to use the conjugate. In general, algebraic simplification, where direct substitution fails, will be your next go-to technique. The above listed techniques are the two most common that you'll use. There will be some other identities that we'll use sometimes too, specifically when trig functions show up. Let's go ahead and try to use direct substitution here in this first example and see what happens that tells us that we need to use algebra. So I don't want to do the graphing here. But if you graphed this, you would notice that there's a hole in the graph. So limit as x approaches 2 of x squared minus 6x plus 8 over x squared minus 4. If we graphed it, it would look kind of linear, except there would be a single hole there. So try direct substitution. 2 squared minus 6 times 2 plus 8 over 2 squared minus 4 is 4 minus 12 is -8 plus 8 is 0 over 0. And this is going to be what we call an indeterminate form. That means that we can't use direct substitution. So we're going to have to use algebra. Let's factor the numerator and denominator. X plus 2, x minus 2, x minus 2, and x minus 4. These x minus 2's will cancel. I'm getting close to 2, but never getting there. So this is not actually getting to 0 over 0, meaning that it's a form of 1. It's a non-zero number divided by the same non-zero number. So that limit is going to be the same as this limit. And now I can use direct substitution. That's going to be -2 over 4, which is going to be a -1/2. Now, in this case, where we have a square root in the denominator, we may need to evaluate from the left and the right to see what happens if 2 comes from the left here. This limit actually does not exist here. So we're going to just skip this one for now because of that limit not existing there from the left-hand side. We'll instead do this example where limit as x approaches 1, and we try and do direct substitution, and we get square root of 1 minus 1 over 1 minus 1. 1 minus 1 over 1 minus 1 is 0 over 0, and we say, nope, can't do direct substitution. because we got an indeterminate form here. So let's try and multiply by the conjugate, top and bottom here. Limit as x approaches 1, the square root of x minus 1 over x minus 1. This is going to be the square root of x plus 1 over the square root of x plus 1. Can multiply by anything over itself here that's a form of 1. And the reason that I chose to multiply by the conjugate here is because a plus b times a minus b is going to be equal to a squared minus b squared. And I'm definitely going to get rid of the square root that way. So the square root of x times the square root of x is x. Then we're going to have a positive square root of x and a negative square root of x that will zero each other out. And negative 1 times a positive 1 is a negative 1. And that's going to be the same factor as this x minus 1. I'm going to be left with the square root of x plus 1 down here. And I forgot to write my limit symbol. Shame on me. Limit as x approaches 1 here. So this is limit as x approaches 1 of 1 over the square root of x plus 1 is 1 over 1 plus 1 is 1/2. So don't simplify denominators here. Multiplying things out until you know you have to. You're waiting for that 0 over 0 term to cancel each other out before you evaluate with direct substitution. So let's move on here. Limits of exponential functions and limits of trigonometric functions. Direct substitution can work for both of these function types when evaluating finite limits, meaning that we're not going to infinity or negative infinity. However, oftentimes algebra is required, specifically with trig functions. So finite limits of exponential functions, like if we're because exponential functions are continuous everywhere, we can just use direct substitution. For example, this is going to be 2 to the 0 is going to be 1. This is going to be e to the 0 is going to be 1. And the idea of the slopes of the secant lines approaching the slope of the tangent line. Here we want to know, does that make sense with direct substitution here? Well, let's go ahead and let's look at the function of e to the x specifically. So let's say y equals e to the x, and we have the point 0, 1. And we have, maybe out here, we have 4e to the 4th. So we already evaluated these, but limit as x approaches 4 of e to the x is going to be e to the 4th. It's going to be about 54.6, right? You can look here and see the end behavior of this graph as x goes to infinity of e to the x is going to approach, well, it's going to be unbounded, so we'll later say that that's going to be infinity. But for right now, we're not going to do a whole lot with tangent lines other than to say you could keep bringing this back closer and closer and closer and closer. And what you're going to see about the exponential function e to the x that's really interesting is that if we did that, that the slope here would actually be 1. The slope here, if we did it, would actually be e to the 4th. And that e to the x, this function is special because the slope is the y value for all x's. That's why math majors love e to the x. It's the only function whose y value is its slope at that point for every x value. So you can examine that some more yourself later, and we'll come back and talk about e to the x a whole lot more. Let's look at cosine of x. Cosine of x is continuous at x equals 0. I can draw that part without picking my pencil up off the paper. So limit as x goes to 0. Cosine of x should be cosine of 0, should be 1. Limit as x approaches 0 of sine x. Let's look at sine x. It's also continuous at x equals 0. So they come from the left and the right there. That approaches sine of 0 is 0. And limit as x approaches 0 of tan x. If I look at that graph here, there's all kinds of more pieces of this, but this is pi over 2 and negative pi over 2. As I come from the left and the right, we're getting closer and closer to 0 there. We can actually think of this as the limit as x approaches 0 of sine x over cosine x is equal to 0 over 1 is 0, and that also works, but we can analyze it graphically. So you can know here later the limit as x approaches pi over 2 from the positive side of tan x. So from over here, it's going to be negative infinity. We're going to go down forever that way. And the limit as x approaches pi over 2 from the left over here of tan x is going to be positive infinity. Some of a really important identity for you to remember from pre-calculus. Your teacher probably made lots of noise about this in pre-calculus and said, if you don't remember anything else from your trigonometry part of pre-calculus, remember that sine squared plus cosine squared of an angle is always, always, always equal to 1. Well, we can rewrite this if we need to, like sine squared is equal to 1 minus cosine squared, or we can rewrite cosine squared is equal to 1 minus sine squared. We might need to factor these things into 1 plus cosine and 1 minus cosine, or 1 plus sine and 1 minus sine. We can look at that as a difference of 2 squares like that if we need to, but just know that these are important techniques with trig identities. So trig identities, especially Pythagorean identities, not just sine and cosine, but 1 tangent squared and secant squared, and 1 cotangent squared and cosecant squared. So let's go ahead and look at this one. If I tried direct substitution to plug 0 in, this would be 0 squared over 1 minus 1 is 0 over 0. It tells me do something, right? Well, let's try and multiply by that missing piece in the denominator here. Let's try and get sine squared to show up in the denominator where I've got the 1 minus cosine. Let's multiply by 1 plus cosine, top and bottom here. And that's going to be limit as x approaches 0 of sine squared x times 1 plus cosine x over this is going to be 1 minus cosine squared x. It's going to be my limit as x approaches 0 of sine squared x times 1 plus cosine x over 1 minus cosine squared is sine squared. That will cancel. Give me limit as x approaches 0 of 1 plus cosine x is going to be 1 plus the limit as x approaches 0 of cosine x is 1 plus cosine of 0. is 1 plus 1 is 2. Now let's look at this one. Remember, cosine of 2x is a special double angle identity. But let's just try it first and see what happens with direct substitution. 1 minus cosine of 0 over sine of 0, going to be 1 minus 1 over 0 is 0 over 0, and direct substitution fails. So we're going to need to remember that cosine of 2x is equal to cosine squared of x minus sine squared of x, or is equal to 2 cosine squared x minus 1, or is equal to 1 minus 2 sine squared x. So we're going to want to use the first one here and say that this is 1 minus cosine squared x minus sine squared x, limit as x approaches 0, and then this is sine x. So this is going to be 1 minus cosine squared x minus minus, this is going to be plus sine squared x over sine x. Again, we need to put the limit symbol here. 1 minus cosine squared x is sine squared x. So that's going to be limit as x approaches 0 of 2 sine squared x over sine x. And one of them will cancel. And this is going to be equal to limit as x approaches 0 of 2 sine of x. It's going to be 2 times sine of 0 is 2 times 0 is 0. And that's it for this video. And we'll come back next time and we'll talk about the second part of techniques for computing limits. See you for the next video.